Hello, welcome to this lesson. In this video, we are going to solve this question I have on the screen. The question says, determine the forces in each member of the triangle below using method of joints. Indicate whether each member is in tension or is in compression. Okay, so now let's look at how you are going to solve this question. Okay, so before you can solve this question, let's look at some things that you must know first, okay, to help us solve questions like this. Okay, so to solve questions like this, okay, one thing you have to know is that we consider the whole truss system to be in equilibrium, okay. We consider the system to be in equilibrium, okay. The system is considered to be in equilibrium, okay. So what that will happen is that this is a truss, okay, and then this truss is made of truss members, okay. So if you look at this truss that we have here, I can see that this is the first truss member. Okay, this is one, this is another, this is another, this is another, and then this is another. Okay, so what will happen is that each truss member terminates at the joints. Okay, so for the truss member one that I indicated, it is going to start from here and then end here. Okay, and then the four also starts from this point and then end here. Okay, so that's how you locate the members. So since the whole system is considered to be in equilibrium, that means that each of the truss members too must be in what, in equilibrium, just to keep the whole system in what, equilibrium. So let's take note of this. So those are some of the conditions that are involved in solving these types of what questions. Okay, so let's look at something else that we have to know about these types of questions. So assuming I have a single truss member, okay, let's say I have a single truss member. Okay, this is my single truss member, and then let's say I have a pin here. Okay, I have a pin here, and then let's say a force is being applied on the pin. Okay, in this direction. That's the force is pulling away from the pin. Okay, let's say you have a force pulling away from the pin. What will you say about this? Will you say this force member is in tension or in compression? Okay, all right, so let's look at what this means. So what is actually happening is that these two forces that are applied in opposite direction, okay, they are actually acting on the pin, not what, the truss member. Okay, this is the truss member, this is the truss member, and then we have this to be the pin. Okay, so the forces that are applied were actually applied on the pin. Okay, so one thing you have to know is that if you apply a force on one pin in one direction, the force on the other pin on the other side must be in a direction opposite to the first direction. Okay, you have to take note of this. So now finally, let's determine whether this is in tension or in compression. So you want to know whether the force member, sorry, whether the truss member is in compression or in tension. So because of the direction of the force that are acting on the pin, you may be tempted to say that this member here is in compression, but that's not the case. Let's look at what is actually happening. So for the trusses, what you are doing is that you're actually looking at the internal reactions on the truss members. Okay, that's what we're actually looking at. So let's say from this truss member that I had here, okay, I have cut it into two. Okay, let's say I've cut it into two, and then I have the pin here which is acting in this direction. Okay, and then let's draw the other half too. Let's say this is the other half also. This is the other half. Okay, so this one also I have the pin here. All right, and then you know that the force will be in this direction. Okay, so it's just the same truss member that I have divided into two just to see the internal reactions. So let's consider one part at a time. So we know that the force, the truss member must also be in equilibrium because the whole truss system is in that equilibrium. So if I cut a truss member into two, okay, we are going to have a surface here, right? Okay, so what will happen is that because the force on the pin, okay, is acting in this direction, the reaction forces, okay, the internal reaction force on the truss member will act in a direction opposite to the force on the pin just to keep this uh, piece here in equilibrium, okay, or just to make that piece stable. That's what will happen. So the same thing will happen here also. Okay, the same thing will happen here also. You see this force is moving in this direction, so the internal forces are going to act in this direction to keep this second piece also in an equilibrium position. So we actually consider the direction of the internal forces and not the direction of the forces acting on the pin. So in this case, the internal forces on this truss member will be acting opposite to the forces that are acting pin on the pin joint. So the internal reactions are actually going to be in this direction. Okay, so when this happens, you're going to have this truss member like this. Okay, and then we have the internal reactions acting in this direction. Okay, so what will be happening is that the truss member will be stretched. Okay, the truss member will be stretched according to the direction of the internal forces. So in this case, we are going to see that the truss member is actually in tension. It is actually in tension, and then it is not what in compression. So you actually determine whether it is in tension or compression based on the direction of the internal reaction forces and not the direction of the forces acting on the pin joint. Okay, so let's take note of that. So let's look at the case of compression also. So I have a truss member here. Okay, and then I have one pin here, I have another pin here. Okay, and then let's consider the forces acting towards the pin. Okay, the forces are acting towards the pin. So here also a force is acting towards the pin. Okay, so is that this figure here, okay, is different from the first one, right? I hope you can see that. Okay, so in this case also, what are you going to say? Are you going to see that the force member is in tension or is in compression? So in this case, what will happen is that because of the direction of the forces that are acting on the pin, the internal reactions are going to act in this direction, okay, to keep the system stable. So what will happen is that you are going to see that this force member here is actually what in compression. It's actually under compression. So that's one thing you have to know. And then what will happen is that when you are for the method of joints, okay, you are going to choose arbitrary directions for the forces acting on the pin joints. Okay, so what will happen is that if at the end of your calculation, okay, you get your answer to be positive, that means that the force is in tension. And if you get negative, that means that it is in compression. And then one thing you have to know is that from the explanation I said, if you can see that if you have a pin, okay, and then the force is moving away from the pin, okay, the force is moving away from the pin, then we can see that the pin is under tension. Okay, this is tension for pins. Okay, and then if you have a pin and then the force is pulling towards the pin, then we are going to say that the pin is under compression. So let's take note of this. So we take tension to be positive and then compression or to be negative. Okay, don't worry, you are going to understand this. All right, so from this explanation that I just made, let's go ahead and solve this question. So to solve this question, the first thing you have to do is to determine the external reaction forces. Okay, that's one thing you have to determine before you can go ahead. So we are actually considering the system to be in equilibrium. That means that the sum of all the forces and the moment should be equal to zero. So to find the external forces, I'm going to consider the truss diagram as a whole. Okay, so let me draw the free body diagram of the truss system as a whole. Okay, so this is the truss system as a whole. Okay, and then at point A, this is point A. Let's put point D here. Okay, this is point D, and then this is point C. Okay, this is point C, and then point B is here. So now let's indicate the external forces and then the external reaction forces. So let me actually bring B here. So we have another 10 kilonewton here. Okay, and then we have 60 kilonewton here. And then at point C, because this is a pin joint, we are going to have reactions both in the x and in the y axis direction. So I'll just choose some arbitrary directions for them. Okay, and then I'll name it as CY and then cx. Okay, then we have 60 kilonewton here, then we have 10 kilonewton here, and then for this support, this is a roller support, so you're going to have a reaction only in the y-axis direction. So let's name this as what, ay. So our goal now is to find the reaction forces. Okay, so we have this distance to be 3 meters, we have 3 meters here, we have 6 meters here. Okay, all right, let's continue. So how do you find the external reaction forces? So to find this, you are considering the system to be in equilibrium. So you are going to apply the equilibrium equations, which will be sum of forces in the x-axis direction should be equal to 0. Sum of forces in the y-axis direction also should be equal to 0. And then sum of moment should also be equal to 0. So I'm going to apply these three equations. Okay, but how do we do this? How are we going to do this? So now let's consider the forces in the x-axis direction. Okay, so for the forces in the x-axis direction, we're going to have some of the forces in the x-axis direction. Then looking at the forces in the x-axis direction, you have cx and then the 10 kilonewton. Okay, and then cx is moving in the negative x-axis direction. So we're going to have minus cx, okay, plus the 10, okay, and then let me write this again, plus the 10 kilonewton, and then this should be equal to 0. So and then we are going to have cx to be equal to 10 kilonewton. Okay, that's the value for cx. Let's take note of that. Okay, so now let's focus on the forces in the y-axis direction also. So some of the forces in the y-axis direction, we're going to have ay, okay, minus the 60 kilonewton plus cy. Okay, I think that's all. We have just three forces in the y-axis direction. Okay, so all this should be equal to 0, right? Let me write this again as ay plus cy, okay, minus 60 should give us what, 0. So that's for the sum of forces in the y-axis direction. So you see that we have two unknowns there, which is ay and then cy. Okay, so that means that we have to get another equation, which will definitely be the moment equation. So how are you going to do this? So to do this, okay, you know that you have ay and then cy there. Okay, so what I'll do is that I will take moment about point A. Okay, when I take moment about point A, I will be able to eliminate ay from that equation, which is the moment equation, and then that will help us find what, cy. So let's go ahead. So sum of moments about point A. Okay, so for sum of moments about point A, you know that ay is acting right from point A, so it's not going to cause any moment. So in that case, we've eliminated ay from that equation. So now let's consider the other forces. We're going to consider clockwise moment to be positive and then counterclockwise to be what, negative. The direction depends on yourself, which one you want to make positive or negative. Okay, so considering the 60 kilonewton, that's going to cause a clockwise moment, and then its perpendicular distance from point A will be the 3 meters. So we are going to have 60 times 3, okay, plus, and then considering cy, that will cause a counterclockwise moment. So we are going to have minus cy, and then its perpendicular distance will be 3 plus 3, which will give us what, 6, okay, and then cx also is acting directly on point A, so that will also not cause any moment. Okay, so its moment will be 0. So now let's consider the 10 kilonewton also, that also cause a clockwise moment. So we're going to have plus 10, and then its perpendicular distance from point A will be the 6 meters, which is this 6 meters that we have here. Okay, so that will be times 6, and then all this should be equal to 0. So you see that at this point, if we have an equation with only one unknown, so you can solve for the unknown. So let's go ahead and then look at that. Okay, so our unknown now is the cy. Okay, so let's look at that. So we are going to have 60 times 3, which will give us a value of 180. Okay, minus 6cy. Okay, plus 10 times 6, which is 60. Okay, all this should be equal to what, 0. So then we are going to have 180 plus 60, which will give us what, 240. So we're going to have minus 6cy equals 240, right? Minus 240, sorry. So let's divide both sides by minus 6, divide both sides by what, minus 6. So let's see what you are going to get for cy. So you're going to have CY to what 240 divided by 6. That gives us a value of what 40 kilonewton. So that's the value for CY. Okay, so now that you know CY, we can go back to this equation here and then find what AY, right? So we're going to have AY plus what CY minus 60 to be equal to 0. So we're going to have AY to be equal to minus CY plus what 60, right? So that will be equal to minus 40 plus what 60. So we're going to get AY, okay, to be equal to 20 kilonewton. So that's the value for what AY also. Okay, so now that you know the external reaction forces, you can actually consider the forces acting on each of the pin joints. Okay, so that we will use that to determine the reaction forces in the truss members to tell whether the truss members are in tension or in compression. So let's go ahead and look at that. Okay, so over here you see that at the end of the calculation, I got AY to be a positive value and I got CY also to be a positive value. So that means that the direction that we chose for the reaction forces are correct. Should you have gotten a negative value, that means that we are going to change the direction. So let's take note of that. Okay. So now what I'll do is that we are going to consider the forces acting on each of the pin joints. Okay, we are going to consider the forces acting on each of the pin joints. And as you can see, I don't have much space here, so I will have to free up some space. So let me do that quickly, then we continue. Okay, so let me write the reaction force that we found. We got Cx, okay, to be equal to 10 kilonewton, and then we got Cy, okay, we got Cy, okay, to be equal to 40 kilonewton, and then we got AY to be equal to 20 kilonewton. Okay, let's put them down. All right, so now let me clear this part also. Okay, so now what you're going to do is that you're going to consider the pin joints, okay, separating and look at the forces acting on them. All right, so let me indicate it on the actual figure. So over here we have AY here, right? We have AY here, and then that's equal to 20 kilonewton. Okay, and then over here we have Cx and then Cy, right? And then Cy is equal to 40 kilonewton, and then Cx, okay, Cx is this is the direction actually. Cx is equal to 10 kilonewton, okay, because it is positive. That's why I choose the direction that way. And then which force again? Okay, so that's all. So those are the reaction forces. Okay, so now to consider the forces on each of the joints, okay, what you are going to do is that you are going to consider a joint where we have at least two unknowns and also we know one load value. Okay, that's what you are going to consider. You are going to consider a pin joint that has what at least two unknowns and then at least one known load value. Okay, let's look at that. So in this case, if I consider joint C, we are going to have two unknowns there, and then if I consider joint A also, we are going to have two unknowns there. Okay, but if I consider joint D, we are going to have three unknowns there, so you can't consider joint D. So you can actually start from A or C. Joint B also, if you consider joint B, you're going to have three unknowns there. So you have actually joint A or joint C to start with. So I'll start with joint A. So let's look at what that is going to be. Okay, so we are going to start with joint A, okay? And then before you go ahead, let's look at something here. I'm going to name this the force in this force member as in this truss member as FAB, okay? And then I'll name this as FAD. Then I'll name this as FDC, and then I'll name this as FBC, and then I'll name this as FDB. Okay, so those are the various forces in the truss members, and then those are the force values that you want to find. So let's look at how you're going to do this. So starting from joint A, okay, if I start from joint A, you know that you're going to have just two unknowns, which will be FAB and then FAD. And then since this is a system of concurrent forces, we are just going to use the two force equations for equilibrium. So for this reason, you must make sure that you have at least two unknowns. You don't have to have more than two unknowns because you are going to use just two equations. So you have to take note of that. So we are going to have here to be the 20 kilonewton. Then I'm going to have this to be the FAD, right? And then I'm going to have this to be the FAB. Okay, so let's go what you're going to do next. Let's consider this angle here to be theta because that's the angle that FAB will be making with the horizontal. So all you have to do is to find this angle here, and to do this, we are going to consider this right angle triangle here, where you have 6 here, and then here will be 3 plus 3, right? And this will be theta. So our theta will be equal to the tan inverse of that will be equal to the tan inverse of 6 on 6. That will be equal to tan inverse of 1. Then we are going to get theta to be equal to I'm going to get theta to be equal to 45 degrees. Okay, let's take note of that. Alright, so let's continue. So from here, we can find the component of FAB, right? You can get the S component to be, you can get FAB, you can get FABX, okay, to be equal to FAB, okay, cosine of um, the angle which is 45 degrees, right? And then you can get FABY to be equal to FAB sine of 45 degrees. Okay, we can have this. So now let's consider the equilibrium equations for the forces. You're going to have some of the forces in the x-axis direction to be equal to 0, and then some of the forces in the y-axis direction to be equal to 0. So for the directions that I chose for FAB and then FAD, they were just some random directions that I chose because I can't actually confirm their directions now. So we'll actually confirm the correct directions at the end of the calculation. If you get a positive answer, that means that the direction that you chose uh, was intentional. And if you get a negative, that means what? It was a compression direction that you chose. So looking at joint A, okay, you will see that we considered FAB to be moving away from the joint. That means that you are seeing that what FAB will be in tension, right? And then FAD also is also going to be in tension because they are pulling away from the pin joint. But if at the end of the calculation you get negative answers for any of them, that means that the direction you chose should rather be the other direction, which is the negative direction, not the positive direction that you chose. So let's continue. So to solve for FAB and then FAD, we are going to consider these two equations. So the first one will be some of the forces in the x-axis direction equals 0, and then the second will be some of the forces in the y-axis direction equals what? 0. So let's look at that. So considering some of the forces in the x-axis direction, we have FAD and then the x component of what? FAB. So we are going to have FAD, okay, plus FAB cosine of what? 45 degrees, and then this will be equal to what? 0. So this will be the first equation, but instead there are two unknowns, so we must consider the next equation also. So that one will be some of the forces in the y-axis direction, sorry, some of the forces in the y-axis direction. For that one also, we're going to have the y component of FAB, which will be FAB sine of 45 degrees, right, plus the 20 kilonewton, and then this should be equal to what? 0. So at the end, you're going to have FAB to be equal to minus 20 divided by the sine of 45 degrees. So let's see what you're going to get for FAB. So minus 20 divided by sine of 45, that will give us a value of minus 28.3 kilonewton. So you see that at first we considered FAB to be in tension because it was pulling away from the pin, but at the end we got a negative answer, which means that it is rather in compression, which means that to be pushing towards the pin. So the direction that we chose was not the actual direction, but you are going to indicate this at the end of the solution. So let's take note of that. So at joint A, okay, these are the directions we considered. Consider this direction, and then let me clean the theta from there. Okay, we considered these two directions. Okay, all right, so let's take note of this. Okay, So now that you know FAB, we can find FAD, right, using the first equation. Okay, so let's look at that. So I'm going to have FAD plus FAB, right, cosine of 45 degrees. This should be equal to 0. We know what FAB, so we're going to have FAD, right, minus 28.3 cosine of, okay, 45 degrees. My answers are to one decimal place. Okay, so we might not really get the same answers. Okay, just the difference of the decimal points. So we're going to have FAD to be equal to 28.3 cosine of what? 45 degrees. Okay, so let's see what you're going to get for FAD. We're going to have 28.3 cosine of 45 degrees. That'll give us a value of what? 20 kilonewtons. So that's the value for FAD. So you see that FAD is positive. That means that the direction we chose was actually the correct direction. So let's write down the values we know so far. We know FAB, which is minus 28.3 kilonewton. And then we know FAD, which is 20 kilonewton, right? Okay, so now let's look at the joint that you can consider again. So based on the direction that we indicated on joint A, we are going to have FAD to be in this direction at joint D. Okay, then you're going to choose a random direction for FDC, which will be this direction, and then for FDB also you're going to choose this direction. So you notice that you know the value of what FAD, right? So looking at joint D, the only unknowns that we have will be FDB and then FDC. And then we said that you must consider joints where you have at least two unknowns. So we can consider joint D in this case. So let's go ahead. So considering joint D, okay, let's look at what you're going to have. So for joint D, this is the pin, and they are considering the forces acting on the pin. Okay, we're going to have FDC to be in this direction. The direction you chose was random, so you confirm that at the end of the calculation. You have FDC here, and then you have the 60 kilonewton here, and then we have FDB here, okay, and then we are going to have FAD here. Okay, so you know that FDB is at an angle. Let's give the angle as alpha. Okay, so how do you find this alpha? We can do that by considering this right angle triangle here. We have 6, we have 3, and then this is what alpha. Okay, just like we are going to have alpha here. So how do you find alpha? Alpha will be equal to the tan inverse of 6 on 3, which will be the tan inverse of 2. That's what you're going to get. The tan inverse of 2, that will give us a value of 63.4 degrees. So we're going to have 63.4 degrees. So let's find the component of FDB. We are going to have the x component, which will be FDBx to be equal to FDB, okay, cosine of 63.4 degrees, and then we're going to have FDB y to be equal to FDB sine of, okay, 63.4 degrees. Okay, so let's consider the sum of the forces in the x and then the y-axis direction. So considering some of the forces in the x-axis direction, we're going to have FAD, FDC, and then the s component of what? FDB. So we're going to have minus FAD, right, because this moving in the negative direction, plus FDC, right, plus the s component of what? FDB, that will be plus FDB cosine of 63.4 degrees. This should be equal to 0, right? Let's consider the sum of the forces in the y-axis direction also. So for that one also, the only force that are in the y-axis direction will be the 60 kilonewton, and then the s component of what? FDB. We're going to have minus 60 plus FDB, right, sine of 63.4 degrees. This should be equal to 0. So we're going to have FDB, okay, to be equal to 60 divided by sine of 63.4 degrees. So we're going to have 60 divided by sine of 63.4. Okay, and then that's going to give us FDB to be equal to 67.1 kilo Newton. Okay, so that will be the value of what FDB. So now that you know the value of what FDB, you can substitute it into this equation to get what? FAD, right? So let's sorry, to get FDC, because you know FAD already, so we substitute to find what? FDC. So let's go ahead. So we're going to have minus FAD plus FDC, okay, plus FDB cosine of 63.4 degrees. This should be equal to 0. So the only value you don't know here is the FDC, right? So let's do the substitution. FAD is 20 kilonewtons. So you're going to have minus 20 plus FDC, okay, plus FDB, which is 67.1, multiplying cosine of 63.4 degrees. This should be equal to 0. So let's look at what you're going to get. You have FDC. Let's add minus 20 to 67.1, multiplying cosine of what? 63.4 degrees. That will give us FDC plus 10. Okay, and this will be equal to 0. So then we are going to have FDC to be equal to minus 10 kilonewton. Okay, let's take note of that also. So let's write those two down. Okay, let's write those two down. We know FDB. Okay, we know FDB to be equal to 67.1 kilonewton, and then we know FDC, okay, also to be equal to minus 10 kilonewton. Okay, let's take note of this. All right, so now the only value you don't know will be the FBC. Okay, so to find out, you can consider joint C also. All right, so let's look at that. So considering joint C, we're going to have this direction for FDC, right? And then let's choose this direction for FBC. Okay, so our goal now is to find FBC. Let's go ahead and do that. Let me free up some space first. All right, so let's continue. So looking at joint C, okay, looking at joint C, let's look at what you are going to have. Okay, so for joint C, you are going to have the 10 kilonewton moving in this direction, right? And then you have 40 kilonewton here. This is 10 kilonewton, and then I have 40 kilonewton, okay, 40 kilonewton, and then we chose. Okay, so this 10 is actually positive. Okay, the direction is not supposed to be going that way. Okay, I think I made a mistake with that. It should be this way rather, because you got the answer to be a positive value. Okay, so that should be 10 kilonewton. So same should happen here. Same should happen here. Okay, sorry about that. I'm going to have 10 kilonewton here. Okay, so let's indicate the direction for FBC, and then these two for FDC. Okay, so now let's consider some of the forces in the x-axis direction. We want to find FBC, right? So you can just consider some of the forces in the y-axis direction. You are going to have you are going to have okay you are going to have FBC. Okay, you are going to have FBC. Okay, so you have FBC, okay, plus 40 kilonewton, okay, and then it should be equal to what? 0, right? And then you know that this system must be balanced, okay, and then look at the directions, like they are all moving towards one direction. So before they must be balanced, one must be in an opposite direction. So you're going to have LBC to be equal to what? Minus 40 kilonewton. So that means that the direction you chose for FBC was actually supposed to be what? Pointing downwards. And of course it makes sense, because if it doesn't point downwards, then it is not the forces are not going to be balanced, or you can see that the pin is what? At equilibrium, because the forces are all moving in the same direction. They must be in an opposite direction for them to be balanced. So as a result, you are going to get FBC to be negative 40 kilonewton. So let's put that down. We're going to have FBC to be equal to minus 40 kilonewton. Okay, so let's look at how you are going to determine if the force members are in compression or in tension. Okay, let's look at that. So let me free up some space and clean some stuff from here. Okay, so let's look at what you are going to do here. Okay, let's look at what you are going to do here. I wasn't even supposed to clean those ones. Let me write them here. FAB, and then let me write FAD here, right? And then let me write FBC here, and then let me write FB, okay, FBD here. Okay, I made it FDB rather, not BD. This should be FBD. Okay, so now let's look at how you're going to determine the members are actually in tension or in compression. So now you will see that for FAB, we choose the direction to be going in this direction, and then after the calculation, you got FAB to be a negative value. So that means that the direction we chose was wrong. So it's actually supposed to be in the opposite direction. So you have to clean it and then indicate the actual correct direction, which will be this direction rather. Okay, which will be in this direction. And then considering FAD, you got that same direction. So you are going to leave it that way. So as a result, you're going to have FAD to be moving in this direction at this joint. Okay, it's going to be in this direction because you know they must be opposite. Alright, so now let's consider joint D also. So for joint D, you have FAD. Okay, that direction is correct. And then you have FDC, right? FDC. And then you got FDC to be minus 10, right? You got FDC to be minus 10, which means that that's not the direction, okay, which means that this will be the actual direction, okay, which means that this will be the actual direction for FDC. That's what, minus 10. And then we have what, FAD to be what, 20 kilonewton, right? Okay, and then FDB, okay, FDB was 67.1 kilonewton, which is also positive, so that means the direction we chose was correct. So at the end, we will have to reverse this direction here, okay, to this direction. Okay, you have to reverse it to this direction. Okay, and then this one also will point downwards here. Okay, this is what you are going to have. Okay, and then at joint B, okay, we got FBC, okay, to be minus 40, which means that it is actually in compression. So I'm going to indicate it this way. Okay, and then this one will also be in this direction. Okay, so that's how our final free body diagram is going to be. So now let's determine which one of them are in tension and which one of them are what, in compression. So from the explanation I made earlier on, you know that if the pin is in if the pin is in compression, okay, if the pin is in compression, that means that the force member is also going to be in compression, right? And then if the pin is in tension, that means the truss member is also going to be what, in tension. So looking at the truss member AB, the pin forces are moving in this direction, right? That means that the internal reaction is going to move in the opposite direction, which is this direction here. Okay, so in this case, you are going to say that the truss member AB is going to be in compression. Okay, so let's look at that. FAB will be in compression. Okay, and then let's look at FAD also. For FAD, the internal reactions are going to react in this direction. So FAD is going to be in tension. Okay, and then let's look at FDC also. The internal reactions will be in this direction, they will be in this direction. So FDC will be in compression. Okay, let's consider FBC also. The internal reactions will be in this direction. They are going to be in this direction. So we can say that FBC will also be in compression. Let's consider FDB. Okay, FDB, the internal reactions will be in this direction. So we're going to consider FDB to be in what, tension. So that's how to determine whether a force member is in, sorry, a truss member is in tension or in compression. Thank you very much for watching this video. If you find this lesson useful, please make sure you like the video and subscribe to the channel.